Hi everyone. So in today's lecture we are going to deal with mechanical properties of fluids and experimental skills related to mechanical properties. So this again will be in one take. So let's see all the important concepts very quickly, and as I have been telling earlier also, if you feel that I am going a bit fast, so because of time constraint we have to complete a very big topic within a particular time frame of say 1 hour or 1 hour 15 minutes. So please bear with me, and if you could not understand any particular concept, later on you always have this facility of either pausing the video and making notes of whatever you want to, or you can just play the video at 0.25 or 0.5x speed so that you can hear me a bit slow. Okay, so let's start. So in mechanical properties of fluids, first of all, we should know that when we are talking of fluid is anything that can flow. Now in this particular chapter we will be dealing with ideal fluids or ideal liquid first of all. So in ideal liquids, mainly we will be focusing on liquids. For gases we have dedicated chapters like kinetic theory, thermodynamics and all. Here we will be focusing on liquids. So what is an ideal liquid? Ideal liquid means which is incompressible. Incompressible means density is the same everywhere, uniform density. There are no effects like surface tension or viscosity. There is no friction. The free surface of the liquid, we are assuming that it is not behaving like a sheet under tension. So there is no surface tension. Now first of all we define a term which is called pressure. You all very well know that pressure means when it is actually an effect of force. It's not a vector quantity, it is an effect of force. Whenever we have a thrust force, which is a pushing force acting on a surface normally, then thrust per unit area on the surface is what we call as pressure. Empirical formula is thrust per unit area. Now if pressure is same at all points on the surface, if pressure is same at all points on the surface and they ask you what is the total thrust, so you will simply say the total thrust will be equals to P into A, provided the surface under consideration is a flat surface. If it is not a flat surface, I have written over here that if it is not a flat surface, then in that case what we do, we will take for a curved surface we will replace A by the area of projection or a shadow of the surface along the direction of the thrust. Just to say, for example, if we have say a curved surface like this, and this is the force lines. So you will, if you have a hemispherical surface say here, so when you will take the area, if suppose this is having a radius r, then you will take the projection as a circle. So this area of projection you will replace by A, and this area will be pi r square. Instead of taking the curved surface area, you will take pi r square. Clear? So here next thing is that if pressure varies continuously, if pressure is found to vary continuously over the surface, then in that case we take a small elementary area dA. So elementary area dA at a particular point where the pressure is known to us P, so we will integrate P with respect to A. Now here SI unit of pressure, you very well know that it is Newton per meter square or Pascal. Now if suppose pressure variation is given, and that too you see that pressure is varying linearly, if pressure is found to vary linearly from one extremity or boundary to the other, then in that case simply thrust force, what you have to do is you have to multiply the average pressure by area, where average pressure is the average of the minimum and maximum pressures acting on the surface. P min plus P max by 2 into area. It not only applies here, whenever we have any mathematical function which is having a linear variation, we can always take its average value in a particular interval as y min plus y max by 2. Clear? Now after this we move to hydrostatic pressure. So in fluid mechanics, first we will study about hydrostatics. Hydrostatics means we are considering the fluid to be in equilibrium. So we are considering the fluid to be in equilibrium, that means net force is 0 in that case, and still we are going to take the case of an ideal fluid. But before that I have written that variation with depth h with respect to a selected reference level h equals to 0 on the fluid. Suppose you take any reference level, it is as per your wish. If you take any reference level, you can take the top surface also as a reference. If you take any reference level and you go to a depth h, then the pressure gradient, that is dP by dH, it is given by rho g, where rho is the density at depth h. Now if you instead of depth you convert it into height, So if you are going up, then pressure is found to be decreasing. In that case, if you are writing dP by dH, that is called pressure gradient with height, and that value you won't be writing as plus rho g, you will write minus rho g, where rho will be the density at a height h. So pressure gradient with depth is rho g, pressure gradient with height is minus rho g. Now if you want to find the total pressure fluctuation, so what you have to do, you have to integrate. Okay, so we need to integrate this if density is varying from point to point. But we generally get the case, if I am taking ideal fluid means density is same everywhere. In that case, when you integrate, you simply get a very basic form, hydrostatic pressure difference delta P is equals to rho g delta H. Means if you take any 2 points, just you have to see what is the vertical separation. I am denoting it as delta H. So whichever point is lower, when you are comparing 2 points, lower point pressure minus higher point pressure, that will become equals to rho g H. That's it. Next thing, whichever point of the fluid you are seeing is exposed to atmosphere, it is in contact with atmosphere. For example, there is a vessel open at the top and the top surface is in contact with atmosphere. Immediately pressure is P atm. If you puncture a hole into a vessel, the hole is exposed to atmosphere, so any liquid near the hole, that point pressure you will take as atmospheric pressure. But if you have on the other hand any point in contact with vacuum or free space, in that case you will take the pressure as 0. Now one very important thing, when I am writing the pressure, saying that pressure is P atm or pressure is 0 or so on, that pressure when we find at any point, it is known as, it is given a name, we call it as absolute pressure. Absolute pressure can either be positive or 0. 0 only in one case if it is vacuum, otherwise it is always positive. Now when we compare the absolute pressure with the atmospheric pressure, when we compare the atmospheric pressure and the absolute pressure, the difference of these two, absolute minus atmospheric, we give it a name, we call it as gauge pressure. Now gauge pressure can be positive, negative or 0. When positive, when the pressure at the point is more than atmospheric pressure. When it is less than atmospheric pressure, negative. When it is equals to atmospheric pressure, then in that case gauge pressure is 0. So yes, gauge pressure can be positive, negative and 0 all, but absolute pressure can be only plus or 0. Now when we write P atm, we should know that how to measure. If you want to find the pressure at any point, you should know the value of P atm and P gauge. So for measuring P atm, we have a dedicated device which is called as a barometer, and when we have to measure gauge pressure, we use a device called as a manometer. Now you can see in the diagram I have shown here barometer, where we generally take a barometric fluid, we take it in a vertical glass tube, and then we invert the glass tube into a bath of the same barometric fluid. So what we see, that if it is an ideal or true barometer, here vacuum will be created because there was no trapped air or gas. So it will be vacuum. Now vacuum means here the pressure will be how much? Here pressure will be, this point pressure will become 0. Vacuum means pressure is 0. So here which point is open to atmosphere? Here pressure is P atm. Now this level also pressure will be P atm. When you go up, pressure becomes 0. So P atm minus 0 is equals to rho g h. Using that concept, we get the true barometric height, capital H is P atm by rho g. So if you simply are able to record this H, then you will say that barometric height H will be equals to P atm by rho g. Or conversely, if you know the barometric height and you know the density of the liquid and G value we know 10 meter per second square, we get the atmospheric pressure at that place. This is called as a true barometer. True barometric height for mercury, if you are using mercury as the barometric fluid, you get H is equals to 76 centimeter. If you are using water, you are getting 10 meter. So when these values we are taking generally at the sea level. So when you put any of these values, you will get according to H and rho, then you will get at sea level the pressure of atmosphere is 10 to the power 5 Newton per meter square, which we also call as 1 atm, 1 atmosphere. 1 atmosphere or 10 to the power 5 Newton per meter square. This is the atmospheric pressure at sea level. But what if we work with a faulty barometer? If we work with a faulty barometer, then in that case, when you will invert the glass tube into the bath of the liquid, you will see that the height of the liquid column will be less than the actual barometric height. So this I have denoted as H apparent. The reason is that here trapped air has some pressure, so it will be pushing the liquid down, so we will get a lesser height compared to what we got in a true barometer, right? So here how to find, again this point is P atm and this side is P air. P atm minus P air is equals to rho g H apparent. So you get H apparent is P atm minus P air by rho g. So pressure, true atmospheric pressure minus a pressure of the trapped air divided by density of the barometric liquid into G. This will give you the H apparent value. So this H apparent, as you can see, is less than the true barometric height H. I hope it is clear. Now, apart from this, what we have, J-shaped manometer. Achha, before coming to this, one more important point. Sometimes you will get questions where they will say a trapped air barometer or faulty barometer is taken to different places. If you take to different places, what will happen? The pressure will change. Atmospheric pressure at different places will be different. So pressure of the trapped air will also change. But we consider that situation that temperature is remaining constant. So for trapped air, we can use Boyle's law. Simply remember, trapped air we can use Boyle's law. That is P air into volume of air. You will say how to find volume of air? Total length of the tube minus H apparent. That will be height of the trapped air multiplied with area of cross section. You will get volume. So PV is equals to constant you can use for trapped air. Understood? Next, J-shaped manometer. It is used to determine the gauge pressure. So J-shaped, you can see that this is a tube of the shape of a J. Now here we have connected to a vessel containing a gas. Suppose the gas pressure is P gas and it will push the mercury in the manometer a bit down and it will rise on the other side so that the system is in equilibrium. So under static condition, again you can see if I look at this point and this point, you can see this point is lower. So this point is pressure of gas, this point is atmospheric pressure. So P gas minus P atmosphere. I am again telling P gas here because this is in contact with gas. P gas and this is in contact with atmosphere. So P gas minus P atmosphere is equals to rho GH. So here we get H is equals to P gas minus P ATM by rho G. Whose density we are taking? The barometric fluid, which is rho of Hg. So here P gauge. Now we know that pressure of gas minus pressure of atmosphere. Here I told pressure at any point minus pressure of atmosphere is gauge pressure. So gauge pressure is rho GH. Rho of mercury, this is rho of mercury into G into H. So if you know the value of H, which you can easily record by a scale, and you know the density of mercury 13.6 gram per centimeter cube, you know the value of G, so you get the gauge pressure. Once you know the gauge pressure, once you know the atmospheric pressure, add both, you will get the total absolute pressure at any point. Clear? Let's move to next. Next, we have pressure variation in accelerated ideal liquids. Now, if the ideal liquid is in a vessel which is getting accelerated, so standard cases you have vertical acceleration and horizontal acceleration. So what is the concept here? That when you are accelerating, obviously the pressure will also vary. So what will happen if you have vertical acceleration? You take any 2 points which have a vertical separation of H. So lower point will have more pressure than upper point I told earlier. So here also PB minus PA will become rho G equivalent into H, where G equivalent, just by using Newton's law, G equivalent is G plus A naught if the acceleration is upward and G minus A naught if acceleration is downward. Mind it, this condition A naught should be less than G if it is accelerating downwards, otherwise the liquid will leave contact with the vessel. Okay, so G plus A naught if it is accelerating upwards, G minus A naught if the vessel is accelerating downwards, and the level will be flat only. Now second case is horizontal acceleration. Again, because of inertia and Newton's law, if you are accelerating the vessel, so due to inertia the liquid inside will try to remain like that only in its position. So as a consequence of that, it will try to move backwards because the vessel is moving forward. So you will see the free surface of the liquid. This is the free surface. Free surface of an ideal fluid has a property that net force along the surface, which is called as shear force, it is 0. So once we are asked rigidity modulus or shear modulus of ideal fluid, we say it is 0. It cannot sustain any shear forces. Along the surface there cannot be any force. If there is force, then it will start flowing. So free surface, net force along the surface is 0. So using Newton's law, we see that tan theta, it comes as A naught by G. If you give an acceleration A naught by G. But if both sides you are having HA and HB as the final heights, then HA minus HB by L, length of the tank, that is also tan theta. So tan theta is A naught by G and also HA minus HB by L. Now if they ask you pressure difference between the points A and B, pressure difference between the points A and B, now even though A and B are at the same horizontal level, but A has now become deeper, it is at a depth HA, whereas B is at a depth HB. So PA minus PB, more depth at A, PA minus PB is rho G HA minus HB. But we just saw HA minus HB is A naught G by L, so you get rho A naught L. Students sometimes ask that, sir, how can we remember so many formulas? A very basic case. If you have vertical, you write rho GH, rho into G, G vertical into H, H is the vertical separation. Similarly, if you have horizontal, you will write rho G will be replaced by horizontal accession and H will be replaced by horizontal separation, which is L. Simple way of remembering. And which side you will have more pressure? By inertia. If you are moving forward, in pressure will be more opposite to accession. Always opposite to accession you will have more pressure. And this surface, if you see the pressure variation is always normal to the surface. So if the surface is slant, pressure will vary normally to the surface. Okay. Now coming to what we call as hydrostatic paradox, very famous hydrostatic paradox and hydrostatic thrust on the base of a vessel, very commonly asked concept. So if you have vessels of different shapes, as I have shown over here, 1, 2, 3, 4, and you fill the same liquid to the same height h, and in each case the pressure at the base will be P atm plus rho gh. So it will be same for all, independent of what is the cross sectional area or what is the shape of the vessel. It will not depend on that, it will only depend on h, and I am taking ideal liquid where everywhere rho is same. So same pressure P atm plus rho gh. Now one very important and interesting case, suppose we take the first 3 vessels and we have all of them have the base cross section area is same base area A. Now if we are asked the force on the base, how it is comparable with the weight of the liquid. So pressure at the base is this. So we know that when we are asked force on the base, so I said in the beginning, when pressure is same everywhere, pressure into area will give you the force. So force on the base will become simply P base into area of the base, we can write so. Now if I am writing this and considering first vessel, all the 3 I am considering area is same, and we are neglecting atmospheric pressure also. Now weight of liquid, if you see 1, 2 and 3 same height, which will have more weight, common sense. If you are seeing this one is having vertical walls. What is happening over here? The liquid is getting pressed here, this is pressed, so its volume will be less than this volume, and this is made to expand like this. So it will contain more volume in the given height. So W in 3 will be more than W in 1 and more than W in 2. This is clear. Now if I compare thrust on base in vessel 1, in vessel 1 force will be weight rho g h into A. I said pressure at base is P atm plus rho gh. I am neglecting atmosphere, so only rho gh into A. Clear. But if you see the weight of first liquid, that is also volume into density into G, that will also come as rho A GH only, which is equals to W1. So when we have vertical walls, the weight of liquid in it is same as the force exerted by the liquid on the base. Both are same. Now force is same on each vessel, F1, F2, F3 all are same, rho GHA. But if you compare now with weight, in second case what is happening, you can assume that this is getting pressed. So if it will get pressed, so by third law the liquid will also press the base more. So the base will be pressed more. That means the force on the base will be greater than the weight of the liquid. Third case, you will see force on the base is still rho GHA. But if you compare with the weight, now what is happening when the vessel, if you take vertical walls and you expand it like this, so the liquid is exerting some force on the side walls also. Because of that, what will happen, that the force on the base will be lesser than the total weight of the liquid. So when we have vessel like this, opening like this, lower cross section narrow, upper wide, then in that case the force will be less than weight. Force on the base will be less than weight of liquid. If the upper cross section is narrow and base is wider, in that case more force will be on the base compared to weight of the liquid. And if you have vertical walls, then whatever is the force on the base, same will be the weight of the liquid. Clear? We are neglecting atmosphere in such cases. Now one more important thing, hydrostatic thrust on vertical dam wall. I told in the beginning that if pressure varies linearly, then we can take the, and if you have a flat surface, we can write the force as, thrust force as average pressure into area. So here suppose we have a dam and the top of the dam is open. So here the pressure at point A will be P atm. Now this liquid is having a density rho, this is the dam wall. So at point B the pressure will become P atm plus rho gh, Pa plus rho gh, so P atm plus rho gh. Now thrust force on the wall horizontally towards right, it will be what? Average pressure, which is Pa plus Pb by 2 into area of the dam wall, which is L into H. So Pa is P atm, Pb is P atm plus rho gh. Sometimes in question they will say that the top of the dam wall is covering the liquid, means it is covered. So if it is covered, there will be no atmospheric pressure on the top surface of the liquid. So in that case, we will take the pressure at the top as 0. So pressure at top will become 0, pressure at B will become rho GH. So directly thrust force will become rho GH by 2 into LH. Clear? Let's move to next, Pascal's law. Now Pascal's law, please don't get confused in Pascal's law. Pascal's law says about the excess pressure. Whenever we apply some extra pressure by exerting some force on any cross section of a liquid, but that liquid should be ideal and it should be completely enclosed. It should not be open anywhere, completely enclosed by some surfaces or vessels. So in that case, whatever extra pressure you are applying at any point by virtue of some external force, then that pressure gets identically transmitted to all other points of the liquid or all other cross sections of the liquid. So the best application of this is hydraulic lift, where we can lift very heavy loads by a very small effort. So you can see in the diagram, we have a vessel which has two different cross sections on two sides, and we have fitted pistons over here. On the first piston, whose area I have taken as A1 as small a, other side area is capital A, and we are applying a force which is our effort, and on the other side we have a car which is kept as a load on the other piston. Now inside you have an ideal fluid of density rho. So this I am taking at same horizontal level. So now the extra force F1 will create a pressure over here which is F1 by A. That will translate into same pressure being exerted here also. So that pressure which was F1 by A, this will create a force F2 at F2 over here. Let's call this force here as F2. So this is resulting thrust due to F1 to lift the load. So it will push the load up. So if F2 is more than the load, more than equal to load, so the load will get lifted up. So what you saw that the extra pressure was F1 by A, and this will be equals to F2 by A. So now if suppose capital A is more than small a, very large, then you will say that F2 is also very large than F1. So that means by very small efforts, we can lift very heavy loads. Clear? Next, we have relative density or specific gravity of a substance. These two terms should not be misunderstood and not be confused with. Relative density or specific gravity are very simple things, just the density of any substance in a CGS unit, and then remove the unit. Whatever is left, the numerical value, that is called as relative density or specific gravity. It is unitless. It is a ratio. It is unitless. So here, how we define density of substance divided by density of water at 4 degrees Celsius. We know density of water at 4 degrees Celsius is 1 gram per centimeter cube. So relative density is also that only. So simply it is the density of substance without using the unit, just the magnitude. In which system? CGS system. When we have a mixture of objects, you will be many times seeing mixture of objects. When they ask you relative density of mixture or density of mixture in CGS, both are same. So it is total mass by total volume. You have to write total mass and total volume in CGS units. Now don't be bothered about the units exactly. You have already written in CGS, only write the numerical values of mass and numerical values of volume. Now if you have been given different objects in the mixture have masses M1, M2, M3 and so on, and individual volumes can be written as M1 by relative density of first, M2 by relative density of second and so on. So this is what we get a simple formula for relative density of a mixture. Same is specific gravity. Specific gravity and relative density are same. Now when we have a solid object whose material density is rho gram per centimeter cube, I have written already CGS, and it has cavity. Cavity does not occupy, cavity only occupies volume, it does not have any mass. So when we take that object, now this object becomes a mixture. Why? It is a mixture of the solid part of the object and it is also containing cavity. So it is a mixture of solid and cavity. So I will write relative density of object is mass of object by total volume. Volume of solid plus volume of cavity. Now this relative density will become less than rho, because rho was, what is rho? Rho of the material is mass by complete volume. But here you are seeing that you are mass by volume of the solid, mass by volume of the solid. But here denominator is volume of solid plus volume of cavity. So denominator is more than volume of solid. So relative density of the object will become less. That is why when we take a solid iron, you put it in water, it will sink. But if it has cavity inside, or if it is a empty vessel made of iron, so it will float in water, because this has become an object which is a mixture of air, cavities and the iron. So density will become less, relative density of the object will be less than the density of the material. So in this case, you will remember volume of the object is equals to volume of solid plus volume of cavity. If you add the solid volume plus cavity volume, you will get volume of object. Now we will say, sir, how to find volume of solid? Simple, volume of solid is mass of the object divided by density of the material. So solid part is simply having a volume mass of object by density of the material. Okay. Next, we have Archimedes principle, which says that whenever we have any object which is partially or fully immersed in a liquid, mind it, this is not only the complete statement, partially or fully immersed, but there should be liquid below also. If there is no liquid below, there won't be any upthrust. So liquid has to be present below also. Many times what happens, you will take a solid object and you place it at the floor of the liquid. You won't say that there is buoyant force acting. Why? Because there is no liquid below it which can push it up. So it will remain submerged there. So here there should be liquid present below the object, and net upthrust or buoyant force by a fluid on an object completely or partially dipped in it. Net upthrust means upthrust from the lower side and downthrust from the upper side. The difference will be upwards. Now you will say, sir, why the difference is upward? Very simple. When you go down, pressure increases. So there will be more pressure below the object than pressure above the object. So net upthrust will be upwards. That is called as buoyant force. Mathematical expression for buoyant force is volume of the object inside the liquid multiplied by density of the liquid into G. And this is also equals the loss of weight of object in the liquid or fluid. So if they ask what is the loss of weight of an object, it is simply weight in air minus weight inside the liquid, and that difference is called as buoyant force. Using this concept of Archimedes principle, we can determine the relative density of any substance or a liquid in this particular way. What we have to do, we just take an object whose weight in air is WA inside water when completely submerged. Suppose the weight is recorded as WW. We can record it. Don't say how. If you still ask, I'll say that use a spring balance. You can measure the tension in the spring balance will give you the recorded weight. So recorded weight when it is completely submerged inside water, let's call that as WW. And when the same object is completely submerged in a liquid, let's take the recorded weight as WL. Then relative density of the object by Archimedes principle simply becomes weight in air by loss of weight in water, means WA by WA minus WW. And relative density of the liquid will be loss of weight of the object in the liquid by loss of weight of object in the water. So WA minus WL by WA minus WW, simple. These are two ways by which you can find relative density of the object as well as of a liquid. Next, buoyant force. We should know, many times what students do, they get confused in drawing the free body diagram. They draw the free body diagram of an object in a liquid. They say that, sir, we have shown buoyant force, we have shown say weight, some string is there, tension, everything. But sir, there should be pressure difference also will create force. Array, that pressure difference force is only known as buoyant force. So buoyant force arises due to delta P between any 2 points in the liquid. So it is a consequence of pressure difference, right? And that's why this force is always taken normal to the free surface of the liquid, and that too outwards. Normal to the free surface of the liquid, it will act on the object outwards, trying to push the object outwards normally. Now why I am stressing on the word normally, you will see by the two diagrams which I have explained here. And if the liquid, suppose sometimes they will say that liquid is accelerated. So obviously we have seen if liquid accelerates, pressure will also change, and because of that buoyant force will also change, and buoyant force will be volume of the object inside the liquid multiplied by density of liquid multiplied by G equivalent. For example, I have shown here, we have this vessel which can either accelerate upward by A0 or downward by A0, and we have this object placed in it now which is floating. So here I am just interested in buoyant force. Don't say where is weight. Weight is also there. I am just showing buoyant force. Buoyant force I will write volume inside into density of liquid into G I will replace by G plus A0 if it is accelerating upward, the vessel. And if the vessel is accelerating downward, G minus A0. That's it. Again here also you have to see that G should be less than A0. I am sorry. A0 should be less than G. So A0 less than G. Now if we take the case of horizontal acceleration and then we keep the same ball, then you will say buoyant force will act normal to the surface. So if you can see this is theta, the buoyant force is acting pushing it normal. And what is buoyant force? V in into rho L into G equivalent. What is G equivalent? Under root of G is vertical, A0 is horizontal. under root of g square plus a naught square. By using Newton's law in the frame of the vessel, we can find that g equivalent becomes root under g square plus a naught square. So this will be the buoyant force. Clear? Next. Okay, next we have the concept of flotation. Whenever a body floats, like you can see these two diagrams have shown floats. So floating means that two forces act on it. One is weight of the object, one is buoyant force. So weight of the object is mass of the object into g. G will cancel both sides. We can write mass of the object will become equals to volume inside into density of liquid, or we can write the law of flotation also as volume of the object into density of the object is equals to volume inside into density of the liquid. That's it. So sometimes they ask in question that what is the volume of liquid that is displaced by a floating object. So you will say volume of liquid displaced by floating object is nothing but V inside. And what is V inside? Mass of the object by density of liquid. Simple thing, mass of the object by density of liquid. For example, if we say that object we are taking, say, is ice, I have written over here. If ice floats on water, they will ask what is the fractional volume inside water. So you will say volume inside by volume, total volume. So it will become rho ice by rho water. Rho ice by rho water is how much? 0.9. Relative density of ice 0.9 means the percentage volume of ice inside water will be 90%. Whenever ice floats on water, 90% is inside, 10% is outside. So this we can find the volume of displaced liquid. Now two important cases for floating, either this or this condition should be there. If you have rho of liquid is more than rho of object, it will partially be inside, partially be outside, and it will be floating. Weight is still equals to buoyant force in both these cases. This is partial sinking, partially outside. Now when weight equals to buoyant force and density of liquid is also equals to density of object, then that means that V inside will become equals to V of object. So the entire volume of the object will just lie inside. Just lie inside means if we call it as just float or just sink. If you see in a question given just floats or just sink, means W is equals to B and the entire volume is coming inside. This is the condition. Rho of liquid should be equals to rho of the object. Now very interesting and important case. In case 1, suppose this object which is lighter than liquid, I take it down by applying some extra force. Suppose I have taken up to here and I release it. So what will happen when it is going inside? Since density of liquid is more, so the buoyant force will become more than weight. It will push the object up. So the object will first rise up with an acceleration, buoyant force minus weight by mass. So don't say, sir, buoyant force and weight were to equal. They were equal while floating, but that was partial sinking. So entire buoyant force, if you see here, is not acting. Entire buoyant force will act when the object will be completely immersed. So when you take it down and release, then what will happen? It will get pushed up by acceleration g into rho L by rho object minus 1. Rho of liquid by rho of object minus 1. It simply comes from buoyant force minus weight by mass. After coming here, it will start oscillating, and after some time, if there are viscous forces in the environment, after some time it will stop and it will finally float here. But first it will go down and then it will, first you are pushing it down, it will go up, it will start oscillating, then come to rest finally. Whereas in second case, the scene is very interesting. If you just touch also, it was totally inside. So buoyant force is W equals to W. No more buoyant force cannot change because the entire volume has come inside. So here buoyant force can no more change and it is balancing W. Now if you just touch it, give it a slight push. So when you slightly push something, that means you are giving an impulse. Due to impulse, you are giving it some speed. Now acceleration is to 0. Here we will always have 0 acceleration, and you have given it a slight impulse due to which you gave it some speed. So because of that, it will uniformly move and settle to the base. So it will move uniformly with uniform speed and it will settle to the base. Very, very important case. Next, if the density of object is more than density of liquid, the moment you put it in the liquid, what will happen? It will sink. It will sink down. Now it will accelerate. What acceleration? Just opposite of this. Just flip it. So you will get acceleration is weight minus buoyant force by mass, which will be g into 1 minus rho L by rho object. Here it was rho L by rho object minus 1 into g. Here it is 1 minus rho L by rho object into g. Clear? Now, as a consequence of pressure, we said that as we keep on going down, hydrostatic pressure P naught plus rho gh. I said buoyancy is a consequence of pressure difference. So when we have a object which is immersed in different liquids, immiscible liquids, they cannot be mixed. Suppose as an example, rho 1, rho 2, rho 3, these 3 liquids I have taken. V1, V2, V3, these are the volumes in the different liquids. Now the pressure over here and pressure over here, if you see the difference, what you will say, here the pressure suppose is P1, okay, here it will become P1 plus rho g H1 plus rho g H2 plus rho g H3. This is what you will write, all the rows are given. Now pressure difference, this minus this when you will do, so P1 will cancel, so you will be left with rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3. Now when you will multiply it with the base area, what you will get? Buoyant force. So buoyant force will become volume 1 V1, A into H1 is V1, A into H2 is V2, A into H3 is V3. Simple technique, V1 rho 1 plus V2 rho 2 plus V3 rho 3. Whatever volume it is occupying in different liquids, just multiply by the density of that liquid. Add all into G. So students have confusion, they think that sir, this liquid is exerting this buoyant force, this liquid is exerting this buoyant force. No, it is the total net buoyant force which is exerted from the base like this of the lowermost liquid. Now this I already told about ice. Next we have level change problems, very interesting case, and students some of them do it very quickly, some take lot of time in solving such questions. Very easy concept. If you see level change problems, they will say that the level of liquid will rise or fall. Very easy way of doing. What you have to do, you have to find Vi and Vf. What is Vi and Vf? These are the initial and finally displaced volumes of the liquid. Now if suppose final displaced volume of the liquid is more than initial displaced volume, means later the liquid is displacing more. So where will the liquid particles go? They will go up. So we will say that the liquid particles will go up. So that means the level will rise. If final displaced volume is less, that means the liquid particles will now come down to displace it. So the level will fall. Vf is less than Vi, liquid level falls down. Vf more than Vi, liquid level rises up. If Vf, Vi are same, there is no level change. Now three important cases are there where you can find Vi or Vf for displaced volume. Whenever you are finding displaced volume due to floating object, I told few moments back, volume displaced due to a floating object is mass of object by density of liquid in which it is floating. Second, completely submerged. If an object is completely submerged inside, then its displaced volume is same as that of the object. The object is entire volume is displacing the liquid. So we will take the displaced volume equal to volume of the object, which can also be written as mass of object by density of object. And third case, when ice melts, if ice melts completely, so how much volume will it displace? It will displace a volume equal to volume of water formed. And volume of water formed can be written as mass of water formed by density of water. And mass of water formed will be same as mass of ice melted. So I can write this as simply mass of ice by density of water. So these are three important cases, kindly remember this. Now as an example or two examples I have shown over here. Suppose ice is floating in a liquid in a vessel, melts completely. Now if it melts completely, earlier it was floating, so I will write initial displaced volume as mass of ice by density of liquid. Later when it melts completely, then I will write melted ice, mass of ice by density of water. This is final displaced volume. Now comparison. If suppose liquid is water only, if liquid is water, then Vi and Vf, can you see denominator and numerator both will become same. So Vi will become equals to Vf, so there will be no change in level. Means when ice is floating in water and if it melts completely, there is no change in level of the water. Next, if rho liquid is greater than rho water, if liquid is denser than water, then what will happen? In initial volume, the denominator will become more, so initial volume will be less, final volume will be more, means we will say the level will go up. And if the liquid is lighter than water, denser than ice but lighter than water, in that case what will happen? Final volume will be less than initial, so level will fall down. One more example, very common and asked many a times in different competitive exams. A wooden block has a coin over it and it is floating in water, right? What happens when the coin falls down? Simple, first both were floating. What I said, while floating, displaced volume is mass of floating object by density of liquid. So mass of wood by density of wood, density of water plus mass of coin by density of water. That's it, initial. Now when coin falls, what will happen? The coin will submerge. But what will happen to the wood? It is still floating. So if I write the final displaced volume, due to floating wood, mass of wood by density of water. And due to submerged ice, I said when submerged object, total volume of the object, which is mass of object by density of object. So mass of coin by density of coin. Now here you compare Vi and Vf, you will see the first term is same for both. Second term numerator is same, but denominator is greater here. So denominator more means value will be less. Vf will become less than Vi, so the level will fall down. So as the coin falls down, level also falls down. Okay. So very interesting and important case we have discussed here. Next we come to fluid dynamics. Till now we were focusing on static fluids, now we have flow of fluids, dynamics. So it is flow of fluids. We are assuming, until unless stated, we will assume the fluid flow to be steady and streamlined. Streamlined means it follows a definite pattern. It will follow a definite pattern. It will not haphazardly or randomly move here and there. If the flow is moving here and there, continuously changing with time and randomly changing with time, the flow is called turbulent. But here we are talking of steady streamlined flow. Steady means non-stop, not stopping anywhere. No fluid particles will get collected anywhere, it will keep on flowing. Irrotational means there should be no formation of whirlpools, there should be no angular momentum that the liquid particles are rotating about any axis. No, that should not happen. Irrotational flow of fluid. Ideal fluid means density constant we are taking only. Now the path which will be followed by the fluid particles, we will give names to those paths, we will call them as streamlines. I have shown over here in the diagram also, we will discuss on that. Streamlines. Collection of streamlines of a flowing fluid is called as tube of flow. So you can see that here I am showing the path of different liquid particles, and the collection of all these streamlines is called as a tube of flow. You can see a shape given to tube of flow. It is wider over here and after some time it becomes narrow. Okay. Now streamlines have properties. What are the properties? The streamlines are normal to any cross section of tube of flow. So if I draw two cross sections in the tube of flow, you can see that streamlines are normal to the cross section at every point. Next thing, for steady flow, equation of continuity is obeyed. If we have steady flow, it is not stopping anywhere, so mass rate of flow will be constant or same for all cross section. What is mass rate? Mass rate is density into volume rate, which is given by rho AV, density of fluid into area of cross section into velocity. This value is constant or same through all cross sections. Now if we are talking of ideal fluids where density is constant, then density constant, so mass rate rho AV, rho is also constant, so we will say AV is constant. What is AV? AV will become the volume rate, dV by dt. D capital V by dt is area of cross section to speed, which will become constant. So AV constant, this becomes the volume rate of flow, and this is equation of continuity when the liquid has constant density, and if the density is also changing but steady flow is there, then you will use mass rate as constant, rho AV constant. Now two important cases of applying equation of continuity. If you have a single tube of flow, so if I take these areas A1 and A2, this is V1 and V2, so I will say A1 V1 equals to A2 V2. So that means greater area, in this diagram you can see A1 greater than A2, so speed wise opposite, V2 will be greater than V1. So at narrow cross section the flow will have greater speed. Okay. Now if the tube of flow is splitting into branches, like the flow was like this and it split into two branches or three branches, multiple branches. So in that case the total volume of rate of flow, so incoming flow rate was area of cross section I have taken here A and into V. Now it is getting into split into two parts, so it will be sum of the two volume rates. So this volume rate is A2 V2, this one is A1, this I have taken as A1, area as A1 and this is V1. So volume rate total was AV, AV will become equals to A1 V1 plus A2 V2. If you have three branches, like that only you can write. Next we are seeing, along with the equation of continuity, we use a theorem which is called as Bernoulli's theorem. Bernoulli's theorem is based on the conservation of energy. We are considering lossless cases of the fluids, ideal fluids. So here, based on energy conservation, at any point of for any fluid element in the tube of flow of an ideal fluid, we have mechanical energy per unit volume is constant. So mechanical energy will be equal to kinetic energy, potential energy, and the energy stored by virtue of the work done by pressure, force. So that sum total by volume is constant. So this is written in the term P plus half rho V square plus rho GH is constant. Okay. So we are taking a particular tube of flow, and for that what we have done, we have taken a reference level as per my wish. I have taken H equals to 0. You can take up also, you can take down also. If you take a reference level, remember when you go up you will take H positive, when you come down you will take H negative. That's it from the reference line. Now here I am taking in the tube of flow 2 points here. I have taken considered 1 and 2. So these 2 points, here the cross section area is A1, here the cross section area is A2. Here pressure is P1, here pressure is P2. Speed here V1, V2, and the height with respect to reference level I have taken H1 and H2. So if I say P plus half rho V square plus rho GH is constant, P1 plus half rho V1 square plus rho GH1 is equals to P2 plus half rho V2 square plus rho GH2. This is to be equated, and this is to be used along with A1 V1 is equals to A2 V2. Now mind one important thing, while applying Bernoulli's theorem at 2 points, say 1 and 2, if you see that one of the areas is very large, that means you can neglect the speed of that particular point in the Bernoulli's equation only, not that you will take that point is at rest. No. While comparing 2 points, if one of the area of cross section is large, very large than the other, then the larger area speed can be neglected in that equation only, Bernoulli's equation only. For example, if I say that A1 is very large, so V1 is approximately taken as 0, not everywhere, only in this equation. Otherwise, so if you put in second equation, you will not get any value only. So in this equation, you can take V1 as 0. Just for our convenience, we will neglect that term. Okay. And obviously along with equation of continuity, we will be using that. Now, when we are writing Bernoulli's equation, if you divide the whole equation by rho G, if you divide the whole equation by rho G, then you get 3 more terms. Now rho is constant, so P by rho G plus H plus V square by 2G becomes constant. So P by rho G is known as pressure head. V square by 2G you will get in half rho V square by rho G, you will get V square by 2G. It will be called velocity head, and H, rho G H by rho G will give you H, which is called as gravitational head. If they are asking you velocity head, pressure head and gravitational head at a point, these are the 3 values, and all are in terms of heights only. They represent some height. Okay, remember this name. Now standard cases, there are only 3 cases where you can use, and very simply we can solve the questions of Bernoulli's theorem. Standard cases, now why 3 cases? Because there are 3 terms in the Bernoulli's equation, so 3 cases. First, if you have 2 points where area is same, if area of cross section of the tube of flow is same, that means V is same by continuity equation. If V is same, so half rho V square cancels, you will simply get hydrostatics. So Bernoulli's theorem simply reduces to hydrostatic. Don't waste time in writing equation. Just write P at a comparatively lower point minus P at higher point in the tube of flow will become rho G into delta H. Delta H is the vertical separation between the 2 points. That's it. Second, if you see at 2 points, H is same. For example, if you have a horizontal tube of flow, H is same at all points. So rho GH term cancels. So when you will write that Bernoulli's equation, rho GH cancel, you will get P1 minus P2 is equals to half rho V2 square minus V1 square, and A1 V1 is equals to A2 V2. Now clearly we can say, suppose V2 is more than V1. So if V2 is more than V1 from this equation, so we can say P1 will be more than P2. So that means simple way, where area of cross section of tube of flow is more, V will be less, pressure will be more. More area, more pressure, less speed. That's it. This is the case, and it has very important applications. First one I have written is Pitort's tube. What is Pitort's tube used for? It is used to measure the speed of flow of a river. So we just put that Pitort's tube, this type of tube you can see, L-shaped tube, we dip it in the river, and this Pitort's tube is kept at rest with respect to river. Now what is happening? The river is flowing. The river is flowing. So outside the Pitort's tube you can see I have drawn the lines of velocity. Here everywhere the velocity is equals to VR. Okay, we are not considering any viscosity, ideal fluid. Everywhere the speed is VR, and when the liquid will enter inside, it will hit here and it will go up. Now since the tube is at rest, so liquid inside will become rest. So if it is at rest, it rises up to a height h. So now I can apply Bernoulli's theorem at points 1 and 2. Just outside the tube, V is equals to VR, just inside V is equals to 0. Both are at same level, so I will use P2 minus P1, where speed is more, speed is less, sorry, pressure is less. So V1 is more than V2, so P2 will be more than P1. So I will simply write P2 minus P1 is half rho VR square. Now what is P1 minus P2? We can say, sorry, P2 minus P1. P2 minus P1 you can compare vertically also. Vertically you can compare by rho GH. By vertically, this and this, they are separated because liquid will finally rise and stop here. So vertical difference between the pressure here and here will be rho G into H. This H you can easily read because this is the water level outside the river. So this one you, if you read, so you will say that the river flow speed is simply root 2 GH. Simple. Next application, venturimeter. In general, if you want to measure the speed of a horizontally flowing ideal fluid, either it is a liquid or a gas, you can use a device which is called venturimeter. It has got different cross sections in the tube of flow. At different cross sections of the tube of flow, we dip two capillary pipes, thin pipes. And what will happen? Here the cross section areas are different. So here more area, more pressure. Here less area, less pressure. So to release the pressure, the liquid will rise up in both the limbs. Where will it rise up? Obviously, common sense. Where pressure is more, there will be more rise. So we can read the difference of the two capillary tubes. Suppose it is H. So we will say P1 minus P2 is rho GH. Which rho? The liquid itself, it is only rising. So P1 minus P2 is rho GH. But by Bernoulli's theorem, both points being at same level, P1 minus P2 can also be written as half rho V2 square minus V1 square. So here rho will cancel, you will get V2 square minus V1 square is 2GH and A1 V1 is equals to A2 V2. Two equations, two unknowns, you will get the values of V1 and V2. Simple. Next, gases. Gases, now they cannot be seen, so you cannot use capillary pipes. Instead, we use a J-shaped manometer containing mercury. So same concept here, gas speed V1, gas speed V2. Here more area, here we will say greater pressure, here less pressure. So it will push the mercury down in this left limb and right limb it will rise up. We can read the difference H. So we will say P1 minus P2 is rho GH. But which rho? P1 minus P2, when you are reading from manometer, for manometer I told earlier, we have to take the density of mercury. But by Bernoulli's theorem, P1 minus P2 will be half rho V2 square minus V1 square. Which rho? Rho of gas, because you are applying Bernoulli's theorem to gas. And you are finding pressure difference here by manometer. So in manometer rho Hg and here half rho gas V2 square minus V1 square. One equation in V1 V2, other equation A1 V1 equals to A2 V2. From these two equations you get the value of V1 and V2. Third important case, if 2 points pressure is same. Suppose for example both points pressure is atmospheric pressure, open to atmosphere. So PATM cancels, then rho will also cancel. So entire Bernoulli's theorem will reduce to motion under gravity. Motion under gravity means when you are coming down in gravity, you know speed will increase, when you go up speed decreases. So that's it. V at lower point, whichever point is lower where you are applying Bernoulli's theorem, whichever point is the lower point, V square minus V square at higher point will become equals to 2GH, where H is the vertical separation. Simple. Application. Where we use it in application, best application is efflux of liquid from a narrow hole, where the hole in a tank is narrow, and in standard case we are taking the hole made at the base. We puncture a hole at the base whose area I have taken a small a, which is very very small than the area of the tank. So while writing Bernoulli's theorem, I said that we can ignore the speed of the position 1 because its area is very large. So here pressure will be P1 is PATM, here also hole open to atmosphere PATM. Pressure same, so directly it becomes what? V flux will become, it is lower point, so just by motion under gravity you will write V1 square plus 2G, vertical separation is H. Now V1 I said we have to take approximately 0. Why? Because area of the hole is very small than area of tank, so V1 can be neglected. So only in Bernoulli's theorem, so we get V efflux speed formula as root 2G. So V efflux will become root 2 GH. Now they ask thrust. If liquid will come out, so it will push the vessel back. That thrust force is rho A V efflux square. So if you know V efflux, rho A V efflux square, and this force will be exactly opposite to the velocity of efflux. Whichever direction efflux velocity is just opposite, it will be exerting thrust on the vessel. They ask what is the time taken to empty the tank. By rate law, we can find the time very easy. A, capital A by small a. If the area of the tank is capital A, area of hole is small a, time taken is A by small a under root 2H initial by G. Whatever was the initial height of the liquid in the tank above the hole, that you have to take. So A by A under root 2HI by G. And if they ask you question that no, we don't want time to empty, time to change the level. So in that case, you will find for two different positions subtract. So delta T will directly come. You can see T is proportional to root H. So delta T will become proportional to root HI minus root HF. So if the level has to fall from HI to HF, the time interval will be root HI minus root HF. Then if they ask you that find the value, that also you can find. What you have to simply write, A by small a under root 2 hi by g minus under root 2 hf by g. That's it. So proportionality wise we can write it like this. Next, we have important cases of efflux. Now important cases of efflux, suppose you puncture a hole at a small height h, total height is capital H. So efflux speed will depend only on the height above the hole. How much is the height? This will be capital H minus small h. So you can see efflux speed root 2g capital H minus small h. Now this will become a horizontal projectile and land on the ground. If it lands on the ground at a distance capital R, so we know for horizontal projectile, range will be horizontal speed multiplied by time. Time of flight will be horizontal projectile, time of flight is simply root 2h by g. How much height is below the hole, that will give you the height, will give you the time. So time is root 2h by g. So sometimes they ask what is the maximum range. Whenever they ask you maximum range, first you find the range by equation of parabola. R max is dr by dh equals to 0, because small h is the height of the hole which I can vary as per my wish. I can puncture at different points. So dr by dh 0, when you differentiate, you get small h is equals to h by 2. That means when you puncture a hole exactly in the middle, then you get the value R max is equals to capital H. Okay. And if you puncture two holes at two different positions at height h1 and h2 from the base, then by same concept we can easily prove that h1 plus h2 will be equals to capital H if you want to get the same range. If by puncturing holes at two different positions on the wall, if you puncture at two different positions of the wall and their sum, this height h1 and this height h2, if these two heights we are considering and we want the liquid coming from both to fall at the same point, same range, then in that case the height of the holes, the sum should be equals to total height capital H. Clear? This is very important point. Now one case I have discussed over here. What if the top of the tank is closed by a lid? So if it is closed by a lid, so topmost point will have zero pressure. Now it won't be atmospheric pressure. You cannot apply V efflux is root 2gh. Here what you have to do, you have to apply Bernoulli's theorem. Here pressure will become 0, here pressure is how much? PATM. Now if you apply Bernoulli's theorem at 1 and 2, suppose I take the ground level as h equals to 0. So at point 1 I will write pressure is 0. Large area I will write half rho v square is also 0. Only I will write rho gh. You can see I have written rho gh. When I write at point 2, it is on the base, no rho gh. Half rho v efflux square, yes. Pressure P atmosphere. We write this equation, we get V efflux as 2gh minus 2 PATM by rho to the power 1 by 2. You would have heard many times and seen also as kids experiment. Puncture a hole in a can, put your hand on the top, you will see that water stops coming out. Open tank, it is coming out, but if you close the top, you will see water stops. Because water stops, what is the condition that water will stop? V efflux will either become 0 or unreal. For that, 2gh should be greater than equals to this. If 2gh becomes more than 2 PATM by rho, then automatically the efflux will stop on closing the top. Clear? Very important case. And if you want it to flow even on closing the lid, then 2gh should be 2gh should be more than 2 PATM by rho if you want the efflux to happen. And if efflux is not to happen, then it should be 0 or unreal. For that, 2gh should be less than 2 PATM by rho. Next, we come to what is called as surface tension. Surface tension is another property of a liquid, practically existing property, where we see that leaves float on the surface of water without going inside. So you cannot say that there is buoyant force. It is completely floating atop water. So it is just like the water is supporting the entire weight of the leaf or small insects over it, nothing going inside. So that property has that property of liquid which is exhibited only on the surface of liquid, it minimizes the surface area. So it will pull the molecules closer to each other, so they will form a chain which will not allow easily other things to go past it. So that's why when we hit a water surface, we can hear clapping sound. It is behaving like a sheet. So surface behaves like a stretched elastic sheet under tension. Now on any line or boundary on the free surface of the liquid, if you draw a line or boundary, whatever you take, the total force due to surface tension from each side molecules will be surface tension into length, total length of the boundary. This will be the total force. Each side molecules of the boundary will be pulling the molecules of the other side. Always attractive force. it is always normal to the boundary, whichever boundary you have drawn, always normal to the boundary. And liquid surface tangential. If liquid surface is flat, the force will be along the surface. If it is tangential, if it is curved, then it will be tangential. Tangential and normal to the boundary. Here we have one more important term which is called surface energy. The surface molecules, they are in tension, they are staying atop, they will be constantly pulled down by the molecules inside the liquid, but still they are staying above, so they have some energy, extra energy possessed by the surface molecules, which is called as surface energy. It is simply defined as surface tension multiplied by total surface area. It is uniformly distributed over entire surface area. If surface area is changed by, suppose we change the surface area by delta A, then the surface energy will also change, and that will be delta U is equals to S delta A. Now this S term I have written here also, here also. This is constant for a given liquid. So S can be defined in two ways: force due to surface tension per unit length, or dFST by dl, or FST by L. Total force by total length, or rate of application of force per unit length, or you can write it as energy, surface energy per unit area, or rate of change of surface energy per unit change in surface area. Any way you can write. This is surface tension, which is constant for a given liquid. Now if temperature rises, you should know that surface tension is mainly due to cohesion between the liquid molecules, which are pulling them towards each other. So if you increase the temperature, the cohesion will decrease, surface tension will decrease. Surface tension decreases with increase in temperature. If very small temperature change is there, the variation will be a bit linearly decreasing. But if it is drastically changing the temperature, it will be curved. The variation will be curved. If highly soluble impurities are added, if you add highly soluble impurities like salt to water, then in that case surface tension will increase. But if you add sparingly soluble, sparingly means very small, sparingly soluble impurities like detergents or surfactants, that will reduce the surface tension, which helps us in washing our cloths very easily by this concept, by adding detergents. So liquid drop, meniscus, these are important points. Liquid drop, meniscus of a liquid in a vessel, they all have single surface. When you pour liquid in a vessel, the top surface is the meniscus. That meniscus has a single surface, liquid below it. A liquid drop of a liquid has a single surface enclosing the entire liquid. Soap bubble is an example of an air bubble which is formed in air. It has got two surfaces. Soap film, it also has two surfaces. I have shown here a soap bubble in air. It has two surfaces, one is the inner one outer. Here we have air, outside we have air, here we have soap solution. This side, this part contains the soap solution trapped over here. Now its thickness I have taken a small d, which is very, very small than radius. So if they ask you what is the volume of soap solution is not in the entire volume, only in this shaded volume. You can see this part. Okay, so soap solution volume is surface area 4 pi r square into thickness, simply approximately 4 pi r square into thickness, and outer radius will be equals to inner radius r plus thickness, which we approximately take as r only because d is very, very small. Whereas on the other hand, when we have a liquid drop, liquid drop volume of the liquid will be entirely occupying, so 4 by 3 pi r cube. When we have a bubble formed in a liquid, so that has a single surface. You can see inside a liquid we have a bubble, air bubble. So air is inside, outside liquid. So single surface, remember this thing. Now here, when we write the surface energy, I told surface energy is surface tension into total area. So for a drop, you will write 4 pi r square, surface area multiplied by surface tension. Soap bubble, it has got two surfaces. So 4 pi r square S for inner one, 4 pi r out square S for the outer one. R out and R in are approximately same only. So that's why we approximately write it as 8 pi r square S, inner and outer combined. Whereas bubble inside a liquid single surface, so 4 pi r square into S. Now, surface tension, as I said, it is due to cohesion between liquid molecules. Sometimes they will be given cases where the end drops, they will say come and coalesce. Coalesce means combine. So what will happen? Energy will be released or absorbed. Very, very common sense. By surface tension has a property of minimizing the surface area. And if surface area will reduce, that means energy will reduce, means energy will be released. Now when the drops are coming and coalescing, combining, so they are coming closer. That means surface tension is bringing them close. So surface tension, what it will do? It will minimize the area, so it will reduce the energy, surface energy, so energy will be released. So that's why if n drops coalesce, first by equaling the total volume. 4 by 3 pi capital R cube is equals to N into single drop volume. So capital R cube is equals to NR cube. 4 by 3 pi, 4 by 3 pi cancels. So from here we get one relation. And I said energy will be released. What is energy released? Initial minus final. Initial energy you had N drops. For one drop 4 pi small r square into S multiplied by N. Final you have one single drop 4 pi capital R square S. Then take 4 pi r square common outside. In place of N you can write R cube by small r cube. So you will get 4 pi r square. I am sorry, here S we had left. 4 pi r square into S. And inside capital R by small r minus 1. This is the energy released. On the other hand, if you blow up drop into pieces, then in that case you will give energy. So energy will be absorbed in the process. Okay. And sometimes they say that this energy released, what will it do to the temperature? So if this released energy is absorbed by the drop, then its temperature will rise. So released energy will rise the temperature of the drop. Next, examples of force due to surface tension in case of equilibrium. For example, we have a thin wire U-shaped and we have a thin wire over here which is hanging vertically, and there is a soap film front and back, two surfaces. See my hand, these are the two surfaces, these are holding the wire. Okay, this pen can be treated as wire, I am holding it. So both front and back side will have a boundary boundary length L from front, back side also L. So 2 SL force upwards will balance the load W. So we can find the surface tension S as W by 2L. So soap solution surface tension can be experimentally found by W by 2L. How much weight is hanging divided by 2 times length of the thin wire. Next, if you take a greased needle and you gently place it on water surface, just like you place a needle over a handkerchief. So what will happen? The handkerchief shape will change. Similarly, the water surface shape will change. It has not gone inside, it is just floating atop. So if you see the needle, this side also we have length L going inside, this side also length L. So surface tension force on both length L, force will be upwards. I have taken a small element, that's why I am writing the force as STL. When I write the total force due to surface tension, it will balance the total weight. So in maximum weight case, when it is balanced and it is not drowning, the total force due to surface tension will be vertical. So vertical force total will be what? S into, if you are seeing that you cannot see the length of the needle from the front, length is inside. This side L, this side length, two boundaries, this pen two boundary, one this side, one this side, length L. So 2SL will balance mg, so maximum weight that can be balanced over here, so m max will be 2SL by g. Then we have a sphere which is immersed, there is a difference, it got immersed means it went inside, so there is buoyant force also acting. Now once it is immersed, surface tension will pull it down. So I have shown the force due to surface tension. In this case you can see the arrows, it is pulled down and you will see the boundary is the circular boundary which is in contact with water. Here this circular boundary whose length will be 2 pi r. So surface tension force downward, weights downward, and if it is floating, buoyant force upwards. So buoyant force is W plus force due to surface tension. Put surface tension force 2 pi rs, weight is 4 by 3 pi r cube sigma g, and buoyant force only half volume is inside, that's why I have used 2 by 3 pi r cube rho water into g. This is one example, important example. Next, force required to pull an object lying on a liquid surface. Sometimes you will see that suppose you keep your mobile phone on a table and there was some water below it, when you will try to pick up you will find difficulty because the water molecules are pulling it down. So you will see if a disc is kept, only the outer periphery is in contact with liquid, so force due to surface tension is S into total outer periphery length 2 pi r. So you have to apply a force in excess of weight. This force applied is in excess of weight, means apart from weight, suppose the weight is 10 Newton and surface tension force is 2 Newton, so you have to apply more than 12 Newton. So I am writing this force is in excess of weight, the extra part, so it should be more than 2 pi rs, don't include the weight part, again I am telling. Next, thin ring. Thin ring, if you take a ring, it has two boundaries, inner periphery also outer periphery, even though the radius is same only for inner and outer almost. So 2 pi r outside, 2 pi r inside. Total force due to surface tension 2 times 2 pi rs. So external force to lift ring in excess of weight will be 4 pi rs. Annular disc, suppose you have a disc and you cut a circular portion, inside radius is r in, outside radius r out. Again you have two boundary. So for inner boundary the surface tension force will be 2 pi r in into s, For the outer boundary, it will be 2 pi r out into s. So total force external required in excess of weight will be greater than this value. Clear? Let's see next. Next case, excess pressure. Whenever there is surface tension, there will be excess pressure due to shape of the liquid surface. It won't stay flat, it will become curved, and this excess pressure delta P excess will be, concave side pressure will be always more than the convex side. When I keep my hand like this side is the concave side and this side is called as the convex side. The depressed side is called the concave side. Concave side pressure is more than convex side pressure across any liquid surface. When we have a spherical drop whose radius is capital R, liquid meniscus, when we have a radius of curvature capital R, in such case they are kept in a cylindrical vessel if the liquid is kept. In such case, the pressure difference, excess pressure, is equals to 2s by r. It is found by Laplace equation, and we can also find it by Newton's law for simple cases also, but we will just remember the result 2s by r. So for example, if you have this drop, concave side is inside, outside we have convex. So concave side P in minus P out. P out is generally taken as atmospheric pressure, P out is taken as P ATM. So P in minus P out, it is a single surface, 2s by r. If we have a concave meniscus, liquid kept in a vessel and its meniscus is like this, concave. So concave side up will have more pressure, P ATM will be more than the pressure just inside the meniscus, PA. P ATM minus PA will be the excess pressure, which will be equals to 2s by r. R is the radius of curvature of this meniscus. If you have a convex meniscus like this, so you can see PA will be more, it will push the meniscus outwards. So PA minus PATM will be excess pressure, which will be 2s by r. So depending on the type of meniscus. Single surface, 2s by r. If you take soap bubble has two surfaces. So inside is also air P in, outside we have P out, which is PATM, and in between them we have a soap solution trapped where I have taken the pressure as P. Now for the innermost surface, one spherical surface, P minus P out and inside we will write concave part is P in minus P will become 2s by r and outside will become 2s by r plus d. But I said r plus d is approximately r only. So when you add both, you get pressure difference between the innermost and outer will be equals to 4s by r. So when we have a soap bubble, 4s by r. If the radius are not given same, they have different radii, kindly don't remove r plus d, keep r plus d only. Understood? Write for both inner periphery and outer periphery and add both, you will get the excess pressure. Now if you have a cylindrical meniscus, in case of cylindrical meniscus, you will say where cylindrical meniscus, suppose you take a water drop and press it between two plates like you can see here. The meniscus here is in the shape of a cylinder. So this is a cylindrical meniscus like this. So in cylindrical meniscus, one radius of curvature is infinite and one is r. So in that case, excess pressure formula is s by r. In spherical meniscus it is 2s by r, whereas in cylindrical meniscus it is s by r. Now if we see this curve, suppose the thickness is d, so approximately I can take this as a hemisphere, so I can write 2r is equals to d, again it's not hemisphere, means I'll say in the form of a semicircle. This part can be treated as a semicircle. So 2r is equals to d can be radius of meniscus can be taken as d by 2. So excess pressure formula for cylindrical meniscus is s by r, it will become 2s by d. Next we have contact angle. Now whenever a liquid is contained in a vessel, then you will draw the tangent to the free surface of the liquid and the tangent to the vessel surface, and this angle formed between them, and that angle should be formed inside the liquid. It should not be taken outside, formed inside the liquid between the tangent to the free surface of liquid and the vessel surface. Generally when adhesive forces are the force exerted by other molecules like of that of the vessel on the liquid molecules, then adhesive force greater than cohesive, then generally it is found that the contact angle is acute and we get a concave meniscus, and such type of liquid is called wetting liquid, it will stick to the surface. Example, water in glass. If it is complete wetting, theta c will become 0 degree. Complete wetting theta c is called as, it is 0 degree. Maximum attraction. If cohesive force is more than adhesive, the liquid molecules will pull the liquid molecules in contact more towards inside. So in that case it will try to stay away from the vessel surface. So contact angle becomes obtuse, 90 degree and 180 degree, it will lie in mid of that. So we get convex meniscus, non-wetting liquid. Example, mercury in glass. Water in glass is wetting, mercury in glass is non-wetting. If you see theta c is 90 degree, 90 degree means flat. Flat is called as critical wetting, neither sticking nor getting away, neither hydrophilic nor hydrophobic. So example is water, if you keep in a silver vessel, then it is found to be having critical wetting. Now if we have a cylindrical vessel and you keep a liquid, suppose concave or convex meniscus, whatever is given, for example I have taken concave, its radius of curvature and the radius of the vessel small r and radius of curvature of the meniscus, they are related as, if the contact angle is theta c, you can see I have drawn a tangent to the liquid surface, with the vessel it is making theta c, so r cos theta c is small r, very important. Radius of curvature of meniscus into cos of contact angle is equals to radius of the vessel, very important case. Now capillary rise and fall. If you have a capillary tube, thin tube, open at both ends and you dip it into a liquid, then due to surface tension, if it is a wetting liquid, you will see that compared to outside, liquid will rise inside. And just by pressure comparison and writing excess pressure, we get a very important result. H is equals to, H, this value is equals to 2s by capital R rho g. Capital R is the radius of the meniscus. If you see contact angle we know this is contact angle theta c. So if you put capital R as small r by cos theta c, so you can write 2s cos theta c by r rho g. This is the capillary rise, extra rise, and this equation is given a name, you can remember, it is called as Jurin's equation. Now if the tube is tilted, suppose you tilt the tube, this relation is obtained by equating the pressure vertically. So if you tilt also, there won't be any change in the vertical capillary rise, this height will be same, only the length of liquid in the tube will change, which you can easily find. If you tilt it by alpha, height capillary, this vertical height will remain the same. So you can say L cos alpha is equals to H. This is L, L cos alpha is H, so L can be written as H by cos alpha. This is the very important case which you have to remember. Next, since it is inversely proportional, capillary rise is inversely proportional to radius of the tube. So in that case, if the tube is broader, there will be less capillary rise. That's why if you see here, when the vessel outside was very wide, here there is less rise, inside there will be more rise because it is narrower. So narrower vessel will have more capillary rise. So if you take this shape tube and if you are considering surface tension also, if you pour a liquid, then you will see that the narrower limb of the U-shaped tube will have more liquid height compared to the wider section. If I take here radius is small a and here I take, sorry, here radius is small a and here radius is small b, where I have taken b greater than a. So what will I say from here? The extra difference is due to capillary rise. So you will write the capillary rise for this part and subtract both. So 2s by r rho g formula, I am assuming complete wetting. Complete wetting means radius of curvature on the left side I am taking as a and radius of curvature on the right side I am taking as b. Complete wetting I am taking. So complete wetting means radius of curvature becomes same as the radius of the tube. Why? Because cos theta c will become 1. Complete wetting. So complete wetting theta c is equals to 0 degree. So left and right side 2s by r rho g subtract. So 2s by rho g common, 1 by a minus 1 by b. Next, if the dipped tube is of insufficient length, then it will not flow out, the liquid will not flow out because it will violate the conservation of energy over here, or not the conservation of energy, means it will violate the case that you are giving energy without any particular source. You cannot create energy by yourself. So that's why it will not flow outside. It will change the shape of the meniscus. Capital R and theta c of the meniscus will change. How? If this height, suppose liquid has a property of rising up to a height h0. You are seeing this tube is of sufficient length, where I have written h0 is equals to 2s by r0 rho g. R0 is the radius of meniscus here. right? Theta c is the contact angle. This is whenever length is greater than or equals to h naught, liquid will always rise up to h naught. Clear? But if you keep the length less than h naught, liquid has the tendency to go up to here, but it is not getting that much. So it will come up to here and change its radius. Radius will become r dash, theta c will become theta c dash. But I said h is inversely proportional to r, so this can be written as h into r is constant. It is called as Jurin's law. So we can relate h naught r naught is equals to, here the length is L, L into r dash. Now you know L, you know h naught, then h naught r naught is L into r dash. Now what is r naught? R naught can be written as r by cos theta c, and r dash can be written as r by cos theta c dash. So you can find the new contact angle also from here. And Jurin's law graph, it starts from r naught. If it is the minimum radius of curvature, as you keep on putting it down and down, dipping it more and more down, then height will decrease, radius of curvature will increase. When the height will become completely zero, radius of curvature will become infinite, flat. So if you take the tube and dip it completely up to here, the final radius will become infinite, flat meniscus. We have non-wetting liquid. If you have a non-wetting liquid, then compared to the level outside, inside the level will fall. So same formula, Jurin's equation, 2s cos theta c by r rho g, you will use mod, because theta c here will be, if you see theta c, again you draw a tangent. If you draw a tangent, angle is always taken inside, liquid surface and vessel wall. This is theta c. You can see theta c is obtuse. So if it is obtuse, so you have to take the mod. So there will be a depression instead of rise. Compared to outside level, inside level, 2s cos theta c by r rho g mod, this will be the depression. Another important point, when you have two soap bubbles, they come in contact. They say that what will happen to the interface. So when they are coming in contact, you can see when we write the excess pressure is inversely proportional to radius. Whichever has smaller radius will have more excess pressure. So here P1 minus P ATM will become 4s by A. Here we have P2 minus P ATM 4s by B. Which one will have more excess pressure? B. So when they will come in contact, then the second bubble will push the interface, the common interface, more towards the larger one. So you can see I have shown it like this, shape changes. Suppose its radius becomes capital R. So you can just add these two, P1 minus P2, you will get from here as 4s, subtract both, P1 minus P2, I think I have made a small mistake over here. P1 minus P ATM is 4s by A, P2 minus P ATM is 4s by B. Now, which side has more pressure? P2 has more than P1, because concave side is P2. Please, with this, P2 minus P1 will become 4s by R. And how to get P2 minus P1? Just subtract 2 and 1. So when you subtract 2 and 1, you will get P2 minus P1 in terms of A and B, and here you are getting P2 minus P1 as 4s by R. When you combine, you get capital R is AB by B minus A. Radius of the contact interface is AB by B minus A. Next, okay, final topic we come to, viscosity. Viscosity is nothing but fluid friction. It opposes the relative motion between liquid layers in contact, and it also opposes the motion of any object inside the liquid. Now, viscosity in liquids, it decreases if you increase the temperature. The liquid layer cohesion will decrease, so viscosity here decreases. But in case of gases, there will be more number of collisions due to increasing temperature, so it will provide greater resistance, that means viscosity will increase. In gases, the viscosity will increase if temperature rises, in liquids it will decrease. Now expression, there are two expressions for viscous drag or viscous force. One is if a thin layer of viscous liquid is trapped in between two plates, one plate is moving plate, one is a fixed plate. Area of each plate is A, and liquid layer, you can see it can be taken as a thin layer whose thickness I have taken as D. Coefficient of viscosity we will define a term eta, and the topmost layer is in contact with the moving layer. Property of such liquids, these are called as Newtonian liquids. Whichever layer of the liquid is in contact with a surface, the velocity of that layer will be same as that of the surface. So topmost layer will have same velocity as the moving plate, which is V0. Bottommost layer will have a same velocity as the fixed plate, which is 0. So when you come from top to bottom, the velocity you can see is decreasing, and finally here it is becoming 0. So here the average force which will be exerted by this layer of liquid on the moving surface will be opposite to V naught. So it will be backwards. If V naught is forward, it is backward. It is given by eta, area of the plate in contact, into difference of the fixed and moving plate speed. So here you will get V naught divided by thickness of the layer D. Eta is called coefficient of viscosity of the liquid. CGS unit is poise, SI unit is decapoise or poiseui. So 1 decapoise is 10 poise. Whenever you are solving questions, be careful with the unit. If you are using, if they have given poise, convert into decapoise first. So this is to be remembered. Next expression for viscous force is when we have a spherical object like a ball moving inside a viscous fluid. Here we use what we call as the Stokes law, dimensionally obtained law. So when we have this object, if at any instant its velocity is v, the viscous force will be always opposite to instantaneous velocity. Its expression is 6 pi eta r v. The outer radius is here r, so 6 pi eta r v. Now if object whose density is sigma is released from rest in a tall column of viscous fluid whose density is rho and coefficient of viscosity is eta, then what will happen at any instant if you write the acceleration? So you will say weight downwards, buoyant force upwards, it is moving down, viscous force upward. So acceleration will be weight minus buoyant force minus viscous force by mass, where downwards. Now when acceleration will become finally 0, when will it become 0? When viscous force will balance W minus B. W and B are constants here inside the liquid. So when viscous force grows with speed and becomes equals to W minus B, acceleration will become 0. At that time V will become constant, that is called as terminal velocity. When you will put acceleration 0, from this expression you know what is viscous force, what is weight and buoyant force. From there you can get the expression for terminal velocity. In next page we have seen written that. Let's quickly see. So that terminal velocity comes as 2g r square by 9 eta sigma minus rho, provided sigma is greater than rho. So this is called as terminal velocity. So what happens when we write the differential equation and integrate it, we find that velocity time graph, velocity increases exponentially from 0 to terminal velocity. Means after a long time it will attain terminal. Whereas acceleration decreases exponentially. The acceleration is decreasing exponentially and finally becomes 0, and velocity grows exponentially and finally becomes Vt. Very, very important point. Next very, very important thing, if the density of the object is very large compared to density of the fluid, we will neglect the buoyant force simply. For example, metal balls are moving in water, raindrops are moving in air, you can neglect buoyant force. Now in such cases they give a very important question is asked. Suppose there are n drops, each one is having radius small r. They are all moving with terminal velocity v naught each. Now if they collise total volume conserved, so and they form a single drop of radius capital R. So we can write that n small r cube is equals to capital R cube. Now also we know terminal velocity is directly proportional to square of the radius. So we can say velocity of big drop by small drop will be square of the radius ratio. So velocity of each big drop, final big drop will be capital R square by small r square into V naught. But what is capital R by small r? It is n to the power 1 by 3 from this relation. So capital R square by small r square will become n to the power 2 by 3 V naught. To summarize, if each small drop has a velocity V naught, if n side drops combine to form a big drop, the big drop will have terminal speed n to the power 2 by 3 into V naught. Clear? Last one point, Reynolds number. How to check whether the flow of a fluid, a viscous fluid inside a cylindrical pipe, whether it is steady or steady laminar, means it is following a fixed pattern, or is it turbulent. For that we use a quantity called Reynolds number NR. NR is defined as rho Vd by small n. If the speed has a value V and eta and rho are the coefficient of viscosity and rho is the density of the fluid or liquid and diameter of the pipe is d. So generally if NR value is less than 1000, the flow is steady and laminar. It will follow a fixed pattern. If it is generally more than 2000, different books give different value for this. It is turbulent flow. It will suddenly change. Now if 1000 and 2000, if it is coming in the range, it will suddenly change. The flow is critical. It can any time change from steady to turbulent. The speed at which the transition occurs, means steady to turbulent, that speed will be called as Vc. So suppose you know the Reynolds number and you know that suppose at a particular speed, say 10 meter per second, the speed is going to be changing from say laminar to turbulent, then you can find the particular value of NR corresponding to that. You will see it will lie in this range. Okay. So these are the important concepts which we tried to discuss fast in today's lecture. I hope these all things you found important and will be beneficial for your preparation. Okay, that will be all.